Go for it. Thanks.
Yeah, so hi everyone. I'm Mayam Gupta and I'm working with Vanessa Mirkadi under Professor Jeff Schneider on our project, which is reinforcement learning for self-driving cars. So this will be the outline for the presentation. So firstly, I'd like to introduce you to our problem statement. So our problem statement is to train a self-driving agent using reinforcement learning inside the Carla simulator. So the end goal here is that we want to have an algorithm that we can train on Argo's hundreds of hours of driving logs that they have collected. And this might not actually happen during our capstone, but that is the main idea behind the project. Also, we want to aim for sample efficient algorithms, so that is also a criteria for the algorithm that we develop. So why the motivation behind this is like for using reinforcement learning, there are many motivations, and the first one is that current self-driving cars are highly modular, and each one of these modules needs to be fine-tuned for rare unaccounted for events, or if you encounter new things I want to transfer to a new domain. So this is very engineering intensive, and an end-to-end model, if it can perform well enough, is much more desirable. Also, secondly, we want to have verifiable performance through simulation. So unseen events can be tested this way. For example, the rain in the video, which is it was not trained upon, but it can be tested upon inside simulation. So we can simulate very rare events, and also we can hope to augment the real world data using the simulation if we have a policy that works. Lastly, such an algorithm can scale very easily to new cities, for instance, if because by virtue of being end-to-end, it's less engineering intensive. So I'd like to talk about a few related works. So the first one is CIRL, and this was the first successful deep reinforcement learning pipeline for vision-based autonomous driving that outperformed previous modular approaches and other imitation learning approaches on the Carla benchmark. So they train an imitation learning model, which is the backbone network, and then they transfer these weights and then fine-tune them using reinforcement learning. And this algorithm uses this paper uses the DDPG algorithm. Secondly, this is a more recent paper which is purely imitation learning based, and this achieves nearly perfect results on the Carla benchmark. And what they do is that they train an oracle using simulator input directly instead of using RGB or any form of image representations. And once they have the oracle, they use the abundant supply of ground truth information to train their image based driver, which just takes in the camera input and then learns to drive. So this uses a very large model, and they had to test on a new benchmark. The one thing they mentioned in the paper is that an exciting opportunity for future work is that combining this idea with reinforcement learning and to train systems that actually exceed this expert's knowledge, so exceeding the capability of this expert. So the third paper that I would like to point out is learning to drive in a day. And this was the first real application of deep reinforcement learning to an actual autonomous driving car. But it's worth pointing out that the task here is very simple. It's just lane following, and the network that they use and also the state space that they use for this is very tiny. Also, the dynamic actor is in the scene, and this also uses DDPG. So the key takeaways from this is that current self-driving RL algorithms have tried several algorithms, and since in the end we want to train on driving logs, we need an off-policy algorithm like DDPG or SAC. So the best of such algorithms that have been demonstrated so far is DDPG, but it's very brittle to hyperparameters and has exploration issues. And this was pointed out by the authors of the soft active predictive paper. So that's why we proposed SAC for our work. Also, in general, off-policy algorithms are more sample efficient, which is also one of our goals. So on to the problem setting. Our input state space is either an encoding of an image. It could be an RGB image, or it could be a semantically segmented image. And we could use an autoencoder or a deep network, or it could be a waypoint. The angle to the set trajectory, which we describe using waypoints. So it could be also that. Or thirdly, we could directly query the simulator about things like, is there a traffic light, is there an obstacle in front, what is the angle to the trajectory, etc. And we can input that information. So these are three possible input state spaces, and our output action space is basically the desired speed and steer, which is bounded and continuous, importantly. And once we have the desired speed and steer, we can use a simple low-level PID controller to control the vehicle, which is what we're doing. There are four scenarios in Carla. So the first one is on which we can train and test. So the first one is like going straight, then turning left, navigation along a set path, and navigating a set path with other cars or other dynamic actors. So previously, in the lab, a team has been working on this project and used proximal policy optimization over encoded semantically segmented images along with waypoint inputs. So there were three rewards that they used. Firstly, there was a speed-based reward to get the car rolling. So for every waypoint it collected, it received a certain reward. Secondly, they received a penalty for deviating from the trajectory too much. And lastly, it received a large penalty for collisions. So this method excelled in the first three scenarios, that is straight driving, navigation, and one turn, but it struggles to brake for other cars. So if you see in the GIF, it just crashes at the end, so with the blue object, which is another vehicle. So it struggles in the navigation with dynamic actors part. So what went wrong? So we want to debug this problem. How can we improve this? So this is the flow of the previous work. So either we can improve the representation part, or we can focus on the reinforcement learning part or the algorithmic part. So firstly, we can remove. So one thing we can do is we can remove the errors that can come from representation, and we can focus solely on the algorithmic development. So we can input the manual state space input, that is querying directly the simulator and inputting that. And secondly, what we can do is we can focus solely on the representation part of things, which is done in previous works that I showed using imitation learning, and they do not have such algorithms. They just focus on this using large networks. And once we have a large pre-trained model, we can then hope to fine-tune it, or at least the last few layers using reinforcement learning, and complete the flow. So that should hopefully improve it. So for right now, if you want to focus on reinforcement learning, the algorithm that they used was proximal policy optimization. And what we proposed was soft actor critic. And these two are designed for very different things. So proximal policy optimization is designed to improve the sample complexity of policy gradient algorithms, which is an on-policy algorithm, whereas SAC is designed to improve exploration, which is desirable. And also as a bonus, it's off policy and also expected to be more sample efficient. So for our experimentation, when I will take over.
Can you stop the screen share so that I can?
Yes. Yes.
All right. Okay. So, okay, am I audible and are my slides visible?
Yes.
Yeah. Okay. So as Mayank mentioned, we propose to use SAC algorithm for our experiments. So we are interested in two scenarios. One is navigation, and the other one is navigation with dynamic actors. So firstly, we start off with a simple experiment, which is only navigation. So the state space is just the mean angle to next 5 waypoints, and the reward that we are using is the speed-based reward that Mayank explained, and the distance from trajectory, where we penalize the vehicle if it deviates too much from the trajectory. So in the initial experiments, we observed that PPO performs way better than SAC. So let me explain the plot, what we are plotting here. So the x-axis shows the duration of the training, and the y-axis shows the total reward. So during the training, after every 10,000 time steps, we evaluate the learn policy on 25 episodes set aside, and we count the total cumulative reward on the 25 episodes, and we plot that on y-axis. So here, the higher the reward, the better the algorithm is, and we can clearly see that PPO performs better than SAC. So this is in contrast to whatever is there in the literature, where SAC usually performs way better than PPO. So we would, and also since we like to have an off-policy working, we started to find ways to make SAC better. So firstly, we tried changing the buffer size and the batch size of the number of samples we are taking from buffer, and also the target update frequencies, but none of them gave any significant improvement to reach the level of PPO performance. So, and after that, one of the crucial experiments we tried is changing the entropy coefficient in SAC. So actually, the authors in SAC mentioned that SAC results are very sensitive to this entropy coefficient. So entropy coefficient is nothing but the trade-off we are giving for the agent to go and explore as compared to collecting rewards. So actually, there are a couple of ways of tuning this entropy coefficient. One is we can do a manual search on the values, or we can actually learn this entropy coefficient. This method of learning the entropy coefficient is actually introduced in the second paper of SAC. So we actually tried both of these. We first tried changing the entropy coefficients, but that did not give any significant improvement. And we also tried by using the learned entropy coefficient, whereas it also did not give any significant improvement. So this basically shows that while SAC does very good job on the open AIGM tasks, and in cases if it does not work on well with PPO, changing just the learning rate would often lead to better performance of PPO. But the case is not exactly the same for self-driving. For some reason, that due to the task formulation or maybe the state space representation, SAC is not able to outperform PPO very easily. So then the main hypothesis we had was that SAC is very sensitive to the learned Q values. So the SAC algorithm does very similar style of updates as value iteration, where we first try to estimate the Q value functions, and we try to improve our policy GDL. So as we can see in the loss function of SAC, it's nothing but the KL divergence between the current policy and the distribution learned obtained using the learned Q values. So if the Q values estimates are biased, then there's a very good chance that our algorithm will break and the policy learned will be very suboptimal. So, and this bias can be due to so many reasons. One reason can be like if I'm not providing my rewards properly, or if I'm not scaling the rewards properly. And the other reason which we think is more relevant to our current scenario is that if my observed state space is not sufficient to satisfy the MDP assumption made in the TD learning. So what I mean is what I mean when I say this is that the underlying task might be perfectly solving the MDP assumption, but if I'm only observing a partial state space or some insufficient state space, then it might not satisfy this inherent assumption in TD learning, and that can cause this bias estimate and bias in the estimates and then break the algorithm. So in such cases, Monte Carlo estimates would be a better fit. So one way of reducing this bias in Q-value estimates is by shifting from one-step reward used in TD learning to n-step rewards. So this n-step rewards is basically like a hybrid between the one-step reward and full Monte Carlo rewards. So as you can see in the formulation, in one-step reward, we just take the reward at the current timestamp. We just take the reward at the current timestamp and use the value at time step t+1 to bootstrap. Whereas in n-step rewards, we just roll out the episode for n timestamps and then take the value estimate at the nth timestamp to bootstrap. So using this n-step rewards can reduce the bias, but it comes at the cost of increasing the variance, which we will deal with later. So in the experiments, so as I said that we hypothesize that this is more the problem is more related to the task and the observed state space. Any algorithm which uses this n-step estimates in their algorithm should be affected equally. So these are the results of PPO, and PPO actually uses generalized advantage estimation, which is very similar to n-step advantage estimation, but a little bit different from the n-step rewards. So we thought of first decreasing the n value in the PPO, and ideally we should observe a decrease in the reward count. So which we observed. So we then move. So this is, so the blue line here is SSE, baseline SSE with one step rewards. Now we try to increase the n in SSE, and we were able to observe a significant improvement in the rewards, but still not surpassing PPO. So we went on to further increase the n, and we were able to actually see improvement of PPO rewards. So so one thing we would like to point out here is that we thought of not increasing n too much because we are not currently using importance sampling, and this decision is made after referring to a couple of papers from one from DeepMind and one from Richard Sutton's lab, where they mentioned that ignoring this importance sampling does not really affect the results that much if you take small n values. But this ignoring importance sampling will make the training much faster, because it will basically help us avoid calculation of probability of the actions taken from buffer every time. So since our experiments are already taking like a minimum of 2 days to observe any results, we thought of moving on with ignoring this importance sampling for now. But again, this will be completely fine for small n, but if we increase the large n too much, it will again introduce the estimates will be wrong, and thereby introducing the bias again, and then the algorithm again breaks. So that's the reason why we are not going for large n. And one thing I would like to point out is that in PPO does not suffer from this, because PPO is an on-policy algorithm and there is no importance sampling actually required. So this is one of this problem is mostly specific to SSE. So here are some results. So on the left is the intermediate policy where the car collides at the turning, where on the right it learns to turn successfully for both right and left turns and successfully complete the episode. So to further evaluate our hypothesis, we experimented on a different scenario, and this is a little bit more complex than the earlier one. Here we have a dynamic actor, so the agent has to, so the vehicle has to learn how to stop and to avoid colliding with other actors and to successfully complete the episode. So in the state space, we used 7 other additional variables because the previous state space is not just enough to avoid collisions. So the added state spaces are the obstacle information and the current vehicle's information, and the other variables like this, how far is my goal from my current position, and is there a red light or so on. And in rewards, we have a couple of additional terms. One is collision reward and the other one is traffic light reward. So collision reward is basically saying if I go and collide with any obstacle, then there is a constant negative penalty and an additional negative penalty if I collide it with higher speed. Same goes for the traffic light. If I cross the red traffic light, there will be a constant negative penalty, and if I cross it with higher speed, there will be more negative penalty. So here are the experiments. So this is the curve for PPO, and this is the curve for SSE with n equal to 1, the name SSE. So as you can see, the SSE performance is very suboptimal, and often the rewards are in negatives. So we tried increasing the n, and we can actually see an improvement over the n equal baseline SSE and actually over the PPO too. So we further tried to increase the n to 50, and the results are almost similar with n equal to 25. And on further increasing the n, we actually observed a decrease in the rewards, which we guess is because of the reason mentioned above, that the non-usage of importance sampling is causing, again, bringing back the biasing. So here are some visualizations again. So these are the videos of the policy trained for 4 million timestamps. So as you can see in the left video, the vehicle successfully learns how to stop when it sees other vehicles in front of it, and once they start moving, it also moves. And it also learns to successfully take the turns, and yeah, it basically completes the episode. yeah, as you can see, it stopped again because the other actor stopped in front of it. And it again starts again, and then it again stops and starts. Yeah, and the speed is also very is near the maximum speed. We actually capped the speed to 20 meters per second. So yeah, it's also going at maximum speed and also learning to complete this episode as quick as possible. So as a future work, we would like to compare the performance using smaller batch size while taking the samples from buffer, because that would make our training faster and we could get more experiments done. Currently, the experiments take a lot of time. Like for the case with navigation with dynamic actor scenario, they take like 4 to 5 days to observe any meaningful results. So that is definitely we would like to work on and see if we could make it faster. And the other major problem is that current SSE is a little bit unstable. So what I mean by unstable is that over the course of training, after some time step, we see a dip in the reward curve, and then but it recovers and starts to improve. The main reason we think why this is happening is because, as we said earlier, we are reducing the bias, but at the cost of variance. So if the variance is very high, then basically the gradient estimates, if the gradient estimates are very high, then the network never really converges, and it is possible that the rewards might decrease as we progress in the training. So I would like to point out that this reward is observed only when we take n equal to 50 and not while n equal to 25. And this is consistent with our hypothesis, because we said that as we increase the n, the variance is increased. And we hypothesize that because the variance is increased, there might be more convergence issue, and hence the reward dips. So if you can see the slide here. So in n equal to 5, the reward curve is not that unstable compared to n equal to 50. So we would like to address this, and the way we are planning to address this is by changing the policy laws in SSE. So currently the authors use the term on the left side, and during simplification they ignore the denominator z theta, where z theta is nothing but a normalization constant, which turns out to be the value function. So the reason they mentioned for ignoring this is because the z theta term does not actually contribute anything to the gradient term of the policy network parameters. This is absolutely true, but following the same logic that is used in policy gradients, in policy gradients they use this baseline term, which actually does not have any contribution to the gradient, but it's very crucial to, but it's introduced to reduce the variance of the estimator. So we would like to apply the same logic here and modify the loss function to the one shown in the right hand side by introducing the value function, and the term in this bracket is called advantage term. So since the SSE algorithm already uses this value function, already estimates this value function in their algorithm, we can directly make use of that without any additional computations. And basically, in general, people try to avoid this because the integration is intractable. But if the integration is intractable in the continuous action spaces, but if we are instead trying to estimate the value, there is no reason why we could not use that. But we need to be careful a little bit, because if that is not, the estimation has bias, then it could again be another factor for breaking the algorithm. So we should be careful while doing that, and we plan to do that. And the final thing we are planning to use is to use the prioritized experience replay, where we instead of taking samples uniformly from the run buffer, we take samples which are more likely to make the network learn faster by using some heuristics. So this has been this is a work already published by the DeepMind lab, and we would like to use this to improve the sample complexity. And one obvious thing we would like to do is to move from the manual state space that we are currently using in our experiments to image state space. And unlike the previous experiments in our lab, instead of using the autoencoder representations, we would like to use the pre-trained model that we trained for imitation learning. So the video shows a sample of how the network layer visualizations look like of the network trained in learning by cheating paper. So as you can see, whenever the network stops, the actuations become a little bit sparse, and when it starts moving, the actuations are much more dense. So the network actually learned something on Carla, and we hope that since we are also doing experiments on Carla, that will be helpful to us. So this is our proposed timeline, where in September we would like to wrap up the stability experiments and parallelly start with the image representations. And in October we would like to reduce the work on towards reducing sample complexity, and in November we would like to do the final experimentation, like studying how changing inputs, image inputs may affect the performance. Thank you.
Thanks very much. We're right at the end of time, but maybe we can take a question if there is one.
I just make a quick couple quick comments. One is that one of my students is actually working on this problem of how to deal with off-policy learning with end-step returns. So feel free to get in touch with me about that. I can put you in touch with them. And then I guess I'm curious, like the subtracting the baseline. I mean, that's done more in policy gradient type algorithms as opposed to like DDPG style algorithms, where the goal is to take the gradient of the Q function and use that to update the policy. Do you have any, I don't know if you have any intuition about whether subtracting the baseline would still be useful in that case?
You mean for the DDPG?
Yeah, well, for SAC also, it's kind of similar, right? So you're taking the gradient of the Q function and using that to update the policy. Do you think that subtracting the baseline would still be useful when the policy is updated in that way?
For SAC?
Yeah.
Yeah, so that's actually the thing we are trying to propose. So let me share the slides again. In here, so actually the first version of SSC, which is soft Q learning, actually kind of does this. So they treat this value function as their baseline. So if we remember, like in policy gradients also, they propose using this value function as the baseline, right? So the soft Q learning version also uses very similar thing, like they try to use this value function as the baseline. So that is something we are planning to use in our experiments too. So we hope that that would reduce the variance of the gradient estimates. Does that answer?
I meant more, I'm not sure it will help because of the way SAC does its updates, but we can talk offline about that. That's fine.
Okay, sure.
Okay. Is the next group here?
Yeah.
Okay.
I think we have a 15 minutes break.
Oh, we have 15 minutes break now?
Yeah.
Oh, awesome. I'm sorry, I didn't see the schedule. Okay, so I guess folks can take a break. Yeah, feel free to replenish, get coffee. If we have time, there's actually one question I wanted to ask the last group as well. So I was super curious, this is not really specific to your approach, but in the related work section, you pointed out that for Carla, I guess there's approaches now that essentially, that learning to cheat thing, that I guess by exposing, I was trying to understand that a bit more. So I guess the intuition there is that because you have access to the ground truth, I don't know, parameters of what's actually happening in the world, you can train something that gets 100% accuracy on Carla. Could you sort of walk me through that? So does that mean that, so does it mean it's actually possible to train an agent that just looks at the perceived pixels and then predicts actions, like I guess a sort of a policy agent that actually does perfectly solve Carla?
can I take that question?
Yes, please.
Yeah, sure.
Yes. So the performance that they show is on the Carla benchmark, which is on just 4 scenarios that they have predefined. So they actually nearly beat it. So it's near perfect. So it's like 199. The numbers are like that. But there are other approaches which have done that as well. The toughest one is navigation with dynamic actors. So it does beat that as well, learning by cheating. So they actually proposed a new metric test called the no crash benchmark, on which it does not have perfect performance. But yes, it did beat all the previous works in the standard Carla benchmark.
So can you explain to me the intuition there? So is the idea that when perception becomes so trivial that you see everything in the ground truth, sort of in the ground truth world, then it's easy to solve?
Okay, let me share my screen again to that slide. Yes. So what they do is they query the simulator for a simplified version. So they just have a 7-channel input and just binarized versions of, whether there's a traffic light, is it green or is it red? On where's the lane? Where are the other vehicles? And then they train an oracle of some sorts. So this is all done using imitation learning, and this should be fairly easy for the network to learn because the input is so simple and is taken directly from the simulator, and there's no image input here. It's just the simulator input. So they train this, and then they have some kind of an oracle for so that gives the output. So given any situation the agent find itself in, this oracle will tell it how to drive basically. So this obviously has a cap of performance. It's not perfect, and this is also something that they mention by that you could use reinforcement learning to improve on the expert itself. So they're assuming that this expert's output is the ground truth. And then they move on to the RGB input. So they take in the images directly from just RGB image, nothing else. And they feed it the output, like what's it's supposed to drive in this, when it sees this image using the pre-trained oracle. So now you have abundant supply of ground truth, right? So you don't have to actually. So the previous problem was that there was not enough exploration. So the previous works that used imitation learning, there were limited amount of expert driving data, but here you can synthesize as much as you want. So they train this using that, um, but it still has an upper limit of this agent's performance, right? It can never outperform the expert.
I see. And you're always starting with something like that multi-channel input, but of course it's not Oracle. It's the output of a.
It's the output of the simulator on expert trajectories. So they use expert trajectories to train this, but using the input of this multi-channel thing. So you have limited expert data, right? So now you can synthesize expert data using this oracle.
Okay.
So they call it the teacher network.
Because I'm still not following something,
Mm-hmm.
but we can sort of. I'm happy to ask offline.
Oh, sure.
Thank you for the suggestions once again, and would be happy to discuss about the points raised.
Yeah, thank you so much.
Cool. Thanks.
Yeah, thank you.
I'll stop recording.
Okay.